So let's take stock of whatever we did so far. The problem that we're faced with, we have a full column rank tall matrix A. In this example that we did, we had 3 rows and 2 columns, so the rank was only 2, but that's the maximum rank it can have, so it's full rank, full column rank. So for a general B that you take, Ax equal to B will not have a solution because B is not guaranteed to be in the column space. So our strategy is to project B to the column space of A as a B hat. Then we get B hat is equal to Ax hat, or Ax hat is equal to B hat, and that is guaranteed to have solutions because B hat is guaranteed to be in the column space. But the price that we pay here is that we are not actually solving for x. X doesn't exist, there is no solution really, but we are solving for x hat, the best possible solution, the best approximation to the solution. So that is the best we can do. So there is an error involved here, and the error is quantified or represented by the error vector E, which will be the original constants vector minus the projection onto the column space. So now let's think about it slightly differently. We know that the error vector is orthogonal to the subspace that you're projecting to. That is why the projection is the closest one in the subspace. So error is actually orthogonal to the column space. What is the orthogonal complement of column space? The orthogonal complement of column space is the left null space. That we will come to in a second. Whatever I said is fine. We still need more information about how to get B hat such that we can solve Ax hat is equal to B hat. So you need to have some more information about the error perhaps. First thing to note is that E is orthogonal to the column space, which means E is in the orthogonal complement of the column space. What is orthogonal complement? Orthogonal complement is the set of all possible vectors orthogonal to a subspace that you're talking about. And what is the orthogonal complement of the column space? That is the left null space. So here is where the left null space, that is coming to it on its own, and then the error is a member of the left null space. Now, how do you solve the bunch of linear equations, the system of linear equations, when it is actually not solvable? We say that the error vector is orthogonal to the subspace, the red plane. What that means is that the error vector is orthogonal to each one of the basis vectors. Is orthogonal to AI. That means AI transpose E is equal to 0. That is the definition of orthogonality. Error vector is orthogonal to each one of the basis vectors. So you have the vectors transposed as rows, and then you have the error vector, and that says something like A transpose and error vector multiplied will give you the 0 vector. What does that mean? Ax equal to the 0 vector, A is equal to the 0 vector. That will mean that X is in the null space of A if you have A transpose Y is 0. By the same analogy, or just looking at the symbols there, you can say that the Y vector now is a member of the null space of A transpose, and that null space is the left null space. So that basically means that the error is actually in the left null space, which we saw because it is orthogonal to the column space by definition. And anything that is orthogonal to the column space is in the orthogonal complement of the column space, and the orthogonal complement of the column space is the left null space. Error vector is in left null space. Since E is in the left null space, E is the same, and also because E is the same as that, E is a B minus B hat, which is B minus A times X hat. So this is the error, and A transpose times E is equal to 0 as you have here. So A transpose times B minus A X hat is equal to 0. So all these things might look a little complex to you, but this is what it is. It is just substituting for E in this equation from the definition of E. E is the difference vector between the projection and original vector that you're projecting. And what it gives you is something quite interesting. It's A transpose B minus A transpose A X hat is equal to 0. Rewrite it, taking one to the other side. What we were trying to solve was Ax equal to B, which we could not solve. Now it looks like you just multiply with A transpose on either side, then suddenly this is actually solvable. But of course you don't get the solution because it's no solution, but you get the best possible solution. So this is the recipe for actually solving. So if you have a matrix A, part of a data matrix, and you have some B constants vector, you know that there is no solution. Ax equal to B doesn't have a solution. All you have to do is to multiply both sides on the left with A transpose, then suddenly magically it becomes solvable. Okay, that is not solvable. Multiply the coefficient matrix on the left with A transpose and the constants vector on the right hand side also, then suddenly it is solvable. So this is what you have to remember. So if you stare at it a little bit, you can see that this is actually what we call the gram matrix, and in our case we had many more rows than columns, and the rank was n. So A transpose A is n by n matrix and its rank is n. We proved at some point that A transpose A, A transpose will all have rank, the same rank. And in this case A has the rank n, so A transpose A also has the rank n, and the size is n by n. So if this is A transpose A, the gram matrix is a full rank matrix. So it can be inverted. That is important, which is why we said this is solvable, because A transpose A can be inverted. And it is symmetric also. It's got other properties which we might, I think we'll talk about it in 2 weeks' time. The smaller matrix is full rank, square, symmetric. We will later call this a positive definite matrix also. So let's look at the properties of the projection matrix once more. How do you get the projection to begin with? So we'll use the projection matrix. So we have the equation Ax equal to B multiplied by A transpose so that it is solvable, and we have the hat here. So we get X hat, the solution is A transpose A inverse, it is invertible, it's a square invertible matrix, times AT times B. We also have Ax hat is equal to B hat, because that is the definition. So this is what we started with, Ax hat is equal to B hat. X hat, remember, was the collection, the set of scalar multiples that of the basis matrix A that will give you the projection in the case of the two-dimensional example that we did. So B hat is equal to Ax hat. X hat we already have here. So we just have to multiply by A. Then we get an interesting thing here. B hat is equal to A transpose A inverse, A transpose B. You get something that is quite interesting. Looks complicated, but if you think about it, we had the projection matrix for vector A, just for a vector, projecting B onto it. We had the projection matrix A transpose divided by A transpose A. This was a projection matrix. And this we can write as, can split A, and this, remember, this guy in the denominator is just a number. It's a square of the norm, just a number. We can split the top part and then write that as A transpose A. That's just a number. Inverse means as a reciprocal. That's what we have there. A transpose A inverse times A transpose. Just that here I have vector, there I have a matrix. Vector, of course, is a matrix of one column. Here you have multiple columns. Now, if you think about it, if you just look at why not expand it and write it this way, get just B hat is equal to B. So B hat is that is the projection matrix. So this you have to think about. This I'm going to leave to you as an exercise. If I have A transpose A X hat and Ax hat is just B hat and A transpose B, then I have A transpose B hat is equal to A transpose B. Then does that imply B hat is equal to B? Does this imply AB is equal to AC? Does it imply that B is equal to C? That is something that you have to think about, and maybe do this in Sage Math with a couple of examples, construct examples to either prove or disprove this one. Now, what we said earlier about the projection matrix will still hold. If you project twice, whether onto a vector or onto a subspace, projecting twice is the same as projecting once, which means P square is equal to P. So if I take P square, so take P here and multiply by P once more, then you can see that it is actually just P, because this guy and this guy will cancel, because A transpose A is invertible and there is the inverse right there. So this whole thing here becomes just I, and I just disappears. So this thing is just as good as not being there. The rest is just P. P is what they call idempotent. The second one is more interesting. Projection matrix is symmetric also. The proof is, the hint to the proof is here. If I consider A transpose B, this is going to be the same as A transpose B hat. If you take a vector A and B, I want to take the dot product, theta here, and it's the same as taking the projection B hat, which will be B cos theta, and then multiplying by A, that will give me A dot B. And if I just take B hat, which will be just this, and that also is A dot B. So A dot B hat is the same as A dot B, just because of the triangle right there. So I can write this is equal to A transpose P B, because B hat after all is a B hat projection operator operating on B. Now if I project A onto itself, you're obviously going to get A. So if I take A and project it, this is going to be equal to A. If I take transpose on both sides, then I get A transpose B transpose is going to be equal to A transpose. So I can take that guy there, A transpose B is the same as for A transpose, I put this one in there. So I get A transpose P transpose B, and from the blue guy here, I get is equal to A transpose P B. This I say will say that P transpose is equal to P. So this is my proof. So take a look at this proof and see if this is actually true. Well, in any case, P transpose is equal to P will satisfy this condition. So that is the proof. P transpose is equal to P. The two conditions that we have, 1 and 2. So those are the two things that we will use to show that P is symmetric. And again, you can take P transpose, which will be the whole thing transposed. And because of the product rule, the first one will be A transpose transpose, which is A. The second one will be A transpose A, the whole thing inverse transpose, which is the same as the transpose inverse. And that is the same as this. And then the last element will be A transpose. So you just apply the product rule of transposes and the fact that transpose of an inverse is the inverse of the transpose, and then use the fact that A transpose A is actually symmetric, and then you will get that the whole thing is symmetric. Quite neat. So now we were working with a two-dimensional subspace in 3 dimensions, but we can actually generalize this. So this is actually the same as projecting to the column space of A, where A was a 3 by 2 matrix, a full column rank tall matrix, but it applies to any matrix that is full column rank with more rows than columns. So in order to make Ax equal to B solvable for a member of Rm by n, all you have to do is to multiply both sides by A transpose, which is what you have to remember. This is what you really have to remember. So again, you're not actually solving it, you're getting the best possible solution. And this is also called the least square minimization. Do you know where this square thing comes from? Can you think about, actually I hinted at it right in the beginning. Can you think of why this best possible solution is actually least square minimization? Yes, we're using Euclidean norm, and Euclidean norm actually inherently has squares in it. And we're trying to find the smallest error vector and smallest error vector in terms of its Euclidean norm. That's why it is a least square minimization. But we are not actually doing any kind of minimization a la calculus. We're actually doing it in a much more elegant linear algebra way. So let me just list the solutions here. So x hat is A transpose A inverse A transpose B. Again, don't try to memorize all these things, but just memorize that Ax equal to B. The moment you multiply both sides on the left by A transpose, you will get something that is solvable in terms of x hat. That's what you have to remember. That's easy to remember. And then from that you can derive all these things. Projection is going to be Ax hat, and that is, since x hat is right there, is multiplied by A. And the projection matrix is whatever is multiplying B to give you B hat, and that is there. Why not expand it, then do the associativity property, and then write P is equal to I. Why not basically apply product rule of inverses to A transpose A inverse? A B inverse is equal to B inverse A inverse, provided that these two guys do exist. If they are invertible, if they are square and invertible matrices, then this equation actually does work. But in this case, they are not square, so they are not invertible, A and A transpose I mean. So we cannot actually do the expansion. If A happen to be square, what would that mean? And invertible. It would actually mean Ax equal to B is solvable, and A column space is all of Rn. Projection of an n-dimensional vector to Rn is actually the vector itself, and P is actually just the identity matrix, because you're projecting a vector into its coordinate space and you get the vector back. So like I said, it is impossible to find any kind of mathematical inconsistency within linear algebra. It is actually beautifully sewn together. Everything fits together very nicely. So you cannot expand it because A is not a square matrix, so it's not invertible. If A were a square and full rank matrix, then the projection is the same as the vector that you're projecting, because column space is all of Rn, and the projection is actually the same as the identity matrix. Now, there is one little thing that I want to highlight because you might come across this. There are what people call hat matrices. Projection matrix is called the hat matrix because P is the one that takes a vector and gives you its hatted version. So because of that, people call it, especially statisticians, call P a hat matrix. So what it does is it takes a vector and gives you a vector in the column space, the projection matrix. And there is another hat matrix typically called P2 that takes a B and gives you a vector in the left null space, and that is called P2. It's the other hat matrix. It's basically just I minus P. So there is a box in the textbook actually explaining this to you. It's not that critical for our application in computer science, but just in case you read up something online or something, you might hear about hat matrices and you might think that I did not teach you this one. If B is actually already in the column space, then the projection to the column space has to be B itself. And if B is orthogonal to the column space, then the projection is 0. All those things you should verify.